In example 2, we have another physics question. This one involves Boyle's law. And what happens is we've got an equation here, PV equals C, and we're going to calculate some derivatives of this. And the idea is that normally we take derivatives with y's and x's, those being the variables we use, but you can use any variables, and in this section we're going to sort of generalize our derivatives to looking at other variables. So question A says find the rate of change of volume with respect to pressure. So the rate of change of volume, that means the V is on top, with respect to pressure means the P is on bottom. So this is just like a dy over dx, where the V is y and the x is P. And there's two ways I can do this. I can, since the P and the V are on the same side, I can use implicit differentiation. The idea is I'm taking the derivative with respect to P of this whole equation. When I take the derivative of PV, the derivative of P, I've got to use the product rule here. The derivative of P with respect to P is just 1, and then the V stays. When I take the derivative with respect to P of V, I've got to think of V as a function of P, which means that I take the derivative of V, that gives me 1, but then I multiply by dV dP by implicit differentiation. And then I'm finishing the product rule by multiplying that by P. When I take the derivative of C, that's just 0, because C, it tells us, is a constant. And now I want to solve for dV dP, so I'm going to subtract the V over dV over dP times P equals negative V, and then divide the P over dV over dP is equal to negative V over P. So that's the correct answer. But there's another way of doing this, which is I could start by solving this expression for V. So V is equal to C divided by P. And now when I take the derivative with respect to P of both sides, this just gives me dV dP. But here I've got to use the quotient rule. So derivative of the top is 0 times the bottom is P, minus derivative of P with respect to P is 1 times C divided by the bottom squared. So this gives me negative C over P squared. And you may look at those two and say, but wait, those are two different answers. And what's going on here is that this answer has both the variable V and the variable P. V is equal to C over P, so if I take C over P and I plug it in here for V, I end up with this expression right here. And now we'll go on to B. It says the sample of gas is in a container at low pressure and is steadily compressed at a constant temperature for 10 minutes. Is the volume decreasing more rapidly at the beginning or at the end of the 10 minutes? Explain. So this is actually a rather complicated question, and we're going to have to use this derivative that we found up here, the negative C divided by P squared. And the idea here is sometimes if you have a general question like this that's not clear what you're supposed to do, it's nice to just choose some numbers. And I'm going to choose, let's let C equal, I don't know, 900. And let's let P equal 10. And the idea is if I choose these numbers and then I look at what's happening in this situation described here, maybe looking at the actual numbers will give me a better sense of what the overall general trend is going on. And I can answer the question in more generality. So if we have those numbers, then dV over dP is equal to negative 900 divided by 10 squared, so that's negative 900 over 100, so that's negative 9. So because of the negative, that means my volume is actually decreasing as I increase the pressure. And here, we're compressing everything at a constant temperature, so T is held constant. And the question is, what happens as I increase the pressure? So if P increases, say, to, I don't know, 20, or no, let's do P equals 30. That'll give me a nice number. Then dV dP is equal to, I still get that negative 900 on top, but now it's a 30 squared. So that's negative 900 over 900. That's negative 1. So negative 9 means my volume is decreasing at a rate of negative 9 as I increase the pressure. Once the pressure gets bigger, though, I'm still decreasing. My volume is still decreasing, but it's at a lower rate. Instead of decreasing by 9 for every amount of pressure that gets increased, it's now decreasing at 1 for every 1 amount of pressure that's increased. So the question says, is the volume decreasing more rapidly at the beginning or at the end of the 10 minutes? Well, this was the beginning of the 10 minutes. Sorry. And this is at the end. And it's decreasing more rapidly here because it's a larger negative number. So it's decreasing more rapidly at the beginning. And the reason is that as you increase the pressure, if we look at our general expression here, as you increase the pressure, the bottom becomes larger. Because as you increase the pressure, the denominator becomes larger, so the expression gets closer to 0. And what we did here is we looked at some we had a general question. We chose particular numbers, and those helped us figure out what was going on in that situation. And then we were able to generalize and say, oh, this makes sense for the whole thing. Okay, we're going to do one last problem, exercise 3. This shouldn't take very long, even though it looks rather complicated. And I'm just going to say, go ahead and try this one on your own, read the question, and try to work out the answers. And when you're done, you can unpause the video and see what I came up with. So go ahead and pause the video now, work on exercise 3. Okay, this is actually a pretty cool question. I found this, this is an actual real equation that shows up when trying to measure atmospheric scintillation. And what we want to do here, it says find the rate of change of the error with respect to, here, the telescope diameter. So that's finding derivative of E with respect to D, which means I'm taking this derivative here of this function. I'm assuming that D is the variable and everything else stays constant. Because these are all getting multiplied, this whole expression at the end here just becomes a constant that sits there. And all I do is take that derivative of the D. So the derivative of E with respect to D is equal to 0.09, that's a constant out in front, times negative 2/3 D to the negative 5/3. That's my derivative of the D, because that's what I'm taking the derivative of. And then all this other stuff just stays the exact same. 2t to the negative 1/2 times 1 over cosine of z to the 1.75 e raised to the negative h over 8,000. B says find the rate of change of the error with respect to the zenithal distance. The zenithal distance is z, so what I want is the derivative of error with respect to z. Now I'm going to take this exact same derivative that I had before, but now I'm just thinking of the z as the variable and everything else as a constant. So this becomes a 0.09 d to the negative 2/3, 2t to the negative 1/2. Now here I put the 1.75 down, and I get 1 over cosine z to the 0.75. Then I multiply by the derivative of what's on the inside here. Well, 1 over cosine z, that's like a cosine of z to the negative 1. So that's negative 1 times cosine of z to the negative 2 power times derivative of cosine is negative sine. And then I also multiply that. I know I'm running off the page now. By e to the negative h over 8,000. And then my last one is c, taking the derivative with respect to the altitude. So this is going to be dE dH. Everything else stays the same. 2t to the negative 1/2, 1 over cosine z to the 1.75. Remember, when I take the derivative of e to the negative h over 8,000, I just start by writing e to the negative h over 8,000. And then I multiply by the derivative of this. Well, this is just like a negative 1 over 8,000 as a constant in front of h, so I just get a negative 1 over 8,000. That's my answer for that one.